So if you go to the, if you want to, you can go to the YouTube link that is pinned in today's text channel, and you should see about the same thing as the Discord live screen capture. The difference is YouTube has a really serious lag. So yep, I can see it going, and I think the audio should be going too, because I can see OBS actually having a pretty healthy mic level. So I think it is doing okay on the other side as well. All right, we got 1 minute and 10 seconds or so left. So if you got any questions, that you want me to kind of address before the class, this would be a good time to pop those questions. You can also use direct message if you don't want the entire class to see your question. That's perfectly okay. And this is why I really like Discord instead of using some of the other channels. It's just one place, and I can do everything from here. All right, it is time. So I'm going to start with something that might annoy some people, okay? Because from this semester, I have to kind of strictly enforce the prerequisite and also the co-requisite of all the classes that I'm teaching. So what I'm showing you right now is from the catalog. So in the catalog, it's still using the old number, which is Math 370. Math 370 doesn't exist anymore because of certain changes to the math department. So the new equivalent course is Math 372, which I think is equivalent to Algebra 2. So this is the class that you need in order to get into Calculus 1. So that's a prerequisite. The co-requisite is CISP430, which means you have to either have taken CISP430 prior to this semester, or you are already enrolled in CISP430 this semester. Now, if you're on wait list, I'm okay with that for now, okay? But eventually, I need you to show me that you get into CISP430. The reason why I'm enforcing the prerequisite and also the co-requisite requirement is because these things are here for a reason, and they're here because over time we learned that it is important to master these concepts, the concepts in Algebra 2 and also the concepts in CISP430, which is data structure, as we go along in CISP440. And people who do not have the prerequisite or the co-requisite, they usually don't do very well in this class. So it doesn't seem to make sense to me to take classes out of order. So there we go. So I'm gonna close that topic here. I got Rick typing, so I'm gonna wait a little bit for the message to show up on Discord. I'm not seeing anything yet. All right. So what we'll do, the first thing is to go to the syllabus, but I'm not going to read the entire syllabus because I already talked about the syllabus in one of the videos. So that means, I'm assuming that you guys have watched that video and also read the syllabus. So what I'll only be talking about will be things that are specific to this course, which is, section 20, the tentative schedule of topics. This is a really tight list of topics. Typically, I try my best to cover everything that is in the schedule, but a lot of times, I kind of have to choose what I need to leave out of this list here, because there's just not enough time in a semester to cover all of these topics. Now, I wish I have enough time to do it. Now that things are online, I actually might have more time to do it. Okay, so this is the tentative schedule. And what we'll do today is one little thing that might be useful to some of you and may be totally useless to the rest of you. It's called a personality test. MBTI stands for Myers-Briggs Type Indicator. It's a way for basically a computer program to ask a whole bunch of questions, and it will indicate what your personality type is. The interesting thing about personality types is it ties into occupations that are suitable, that basically play to your strength. So it's something that is kind of useful to do if you want to, if you have time to do it. But it's not mandatory, and you do not need to have to share your result with me. The share folder link is really just going to a particular folder where, you know, if I think, okay, this file is useful to the whole class, you know, I would in the past I would upload to the share folder, but now I'm using Discord. I'll just go ahead and upload, you know, smaller files to Discord. So if you go to the text channel of a particular day, you would typically also find, you know, files that I find useful, and I'll upload those files over there. So with that stuff done, and I'm not seeing any questions in the text channel, I'm going to go ahead and start with Boolean operators in this class. The other things that are not really shown on your side, you know, they're not really essential, and sometimes I look at these documents and go like, they're not really finished, or, you know, I do not want to include those in the class, so that's why they're hidden. But I don't want to remove the links just yet, because I might want to go back in and, you know, edit those documents. So maybe at some point, you know, they will be visible again, just not right now. So what we'll do is we're going to go to Boolean operators, and I'm stopping to update the PDF. So even if you see a PDF link, you know, just kind of keep in mind that the PDF link may not be updated. The reason has to do with the tool that I'm using to generate the PDF is not very accessibility friendly, you know, when it generates the PDF. And there's really no reason for me to generate the PDF anymore, because, you know, once you have the HTML document, you can always print it to a PDF if you want to. So there's no need for me to maintain the PDF version of the documents. The HTML document, you know, on the other hand, is always going to be updated. So use that instead. So there we go. All right, so this is a relatively newly regenerated document, and you can tell from the date. Okay, this was generated like just 2 days ago, because I update my tools, you know, from time to time, and the way they generate the document, you know, the output is a little bit different. And this one I think is more accessibility friendly. For anyone who needs accessibility help, the best thing you can do is to contact our DSPS department first to see if you can arrange resources. All right, cool. So what we'll do is now we just kind of go in and look at all the Boolean operators that you should have known already at this point. All of these operators are introduced, or most of these, okay, they are introduced in C and C++ already. So there should be no surprises until we get to section 4, which talks about other operators that you do not find in C and C++. All right. So I'm seeing some voice activities from certain people who have not muted their mic. So if you have not muted your mic, you might want to do that, you know, because otherwise, you know, oh, thank you. So if you do have something to say, you can just go ahead and unmute and let me know, you know, using the voice channel, or you can type in the text channel where I can, you know, read your text and be able to answer your question. All right. So section 3 talks about, you know, C, C++ Boolean operators that we should know at this point. The way we read this table is kind of a little bit funky, okay? So we break up a table into rows, you know, across like this, and columns, you know, across like this vertically. So this format basically says, you know, if you look at this row here, they're corresponding to y being 0. If you look at this column here, it is corresponding to x being 0. So if I pick a particular cell, let's say this one here, it means I'm looking at x being 0 and y being 1. So that means we are looking at the conjunction of 0 and 1. 0 and 1, 0 meaning false and 1 meaning true, has a result of false. So that's how I write this particular truth table. And then later on, we'll have a slightly different way of looking at a truth table, which is a more conventional way of looking at a truth table. So the shorthand of this table over here is over here, where I basically use the down arrow symbol to mean that these two values, 0 and 1, they apply to variable y, which means this entire row is corresponding to what happens when y is false, and this entire row here is corresponding to what if y is true. I use x and then a horizontal arrow pointing to the right hand side to basically mean that these two values over here, they apply to x. So that means if you look at this column over here, it corresponds to x being 0. When you look at this column here, it corresponds to x being true. So and then the diagonal line is basically saying what happens to these cells over here. They are corresponding to x and y in this case. So conjunction is and the symbol that we use typically in this class, the mathematical symbol looks like a wedge, okay, which is what I use in the table. So if you look into this part over here, you can see that this is the symbol that you're familiar with in C and C++. It is a double ampersand, not a single ampersand. A single ampersand has a different meaning. It is a bitwise and a double ampersand is a logical and. In mathematics, mathematicians would use this kind of like a inverted V symbol to mean exactly the same thing. And so you would find this symbol used in various literature, including algorithms and whatnot. A lot of times we simplify conjunction. Instead of using this symbol, which is a inverted V, we would actually use multiplication, or we will borrow the notation of multiplication for conjunction. And that has to do with conjunction in Boolean algebra has a lot of similarities to multiplication in normal algebra. Okay, there are some weird things you can do in Boolean algebra that you cannot do in normal algebra. So we'll get to those a little bit later. But for now, what I'm going to say is to say that sometimes for convenience, I am going to borrow the notation of multiplication to mean conjunction. So in other words, if I want to say x and y, okay, and I want to use the shorthand, I'll just use xy, which is how you normally write x times y in a math class. So do we have any questions up to this point? Okay, so I'm not seeing any questions. How long would be a good time for me to use before I time out and say, okay, I'm gonna assume there are no questions? You guys can type your answer. About 5 seconds? Yeah, I think that's about right. Okay, very cool. A few seconds. Okay, that's a little bit less specific, but I'm gonna guess around 5 seconds is good. All right, so we are moving on to section 3.2, which talks about disjunction. Disjunction is really just a fancy word for or, okay, for logical or. Now, or is a little bit funky because we have or, and then we have either or exclusive or. Disjunction means just a normal or, okay? So if you look at the truth table, it basically means if you have x or y, if at least one side is a true, then the entire expression is a true, okay? So that's how we use disjunction in this kind of definition. In C and C++, or is used, is represented by two vertical bars, okay? One single vertical bar is what we call a bitwise OR operator, which is not the same as a logical OR operator. So if you're referring to a logical OR, or disjunction, it has to be a double vertical bar. In mathematics, they use a symbol that looks like an uppercase V to represent disjunction. But in this class, a lot of times I would use the shorthand of a plus to represent disjunction. Now, why? It's because disjunction in Boolean algebra actually shares a lot of properties and characteristics as addition in normal algebra. Just like, conjunction is like multiplication, disjunction is like addition, and that's why I'm going to use that notation. So do we have any questions about disjunction, particularly about the notation? Because some people may find it confusing once I start to use multiplication and addition symbol in a Boolean expression. So I'm just checking out the text channel. No questions. All right. So we are moving on to logical negation. Logical negation is the word not in English, and it's a pretty easy one. Okay, not false is true, not true is false. So in this class, I would typically use 0 to mean false and 1 to mean true, simply because they are easy to type, but also because in a lot of higher level math classes, they would also use 0 to represent the identity of disjunction, and then use 1 to represent the identity of conjunction. So 0 and 1 in higher level algebra do not mean the values 0 and the value of 1 anymore. They are basically used to mean, okay, this is the identity of disjunction, which means anything or false is the original anything. And then we use 1 to represent the identity of conjunction, which basically means anything and true is anything. Okay, so that's kind of if you ever get into abstract algebra in a 4-year university, you will come across 0 and 1 as symbols to represent identities respectively for quote-unquote multiplication and conjunction at that point. All right. So moving on, in C and C++, logical not is an exclamation point. An exclamation point is not the same as a tilde. A tilde is also a not, but it is a bitwise not a logical not. In mathematics, if you ask a mathematician, they use this kind of weird little symbol that looks like a minus but with a drop on the right hand side as the symbol for representing logical not or Boolean not. In engineering, if you want to get into computer engineering or electrical engineering, they would put a bar on top of a variable to mean the negated value of that expression. So this x here can be an entire expression. It's just that in this case, we only use one single variable. But you can probably imagine it is difficult to type x with an overbar. So that's why in a lot of circuit diagrams, when they explain something is a negated value of something else, they would use a slash to mean negation. So these are all kind of acceptable ways to represent negation. So in this class, you will find me using just exclamation point to mean negation, simply because it's easy to type on the keyboard. So between conjunction, which is just borrowing multiplication, disjunction, which is borrowing addition, and then we have negation, which is using the exclamation point. That's usually how I express Boolean. This is how I express Boolean expressions. So do we have any questions about section 3 at this point? All right, I'm not seeing any questions. All right, so let's move on to section 4. So section 4 starts to talk about something, weird little operators that we typically have not encountered, okay? Unless you have taken CISP440 from me, then you probably have not encountered this little operator called NAND, okay? So NAND, N-A-N-D, stands for negated and, okay? So if you look at the definition, I don't know exactly why, but the up arrow symbol is used to represent NAND. So if I want to say x NAND y, I use x and then the point up arrow and the y to represent x NAND y. But the definition of NAND is really just the negated version of an AND. Okay, so let me see if I can pop up my okay, so let me get rid of this, go to here. I'm doing some stuff off screen, so you cannot really quite see what I'm doing right now at this point, but I'm now moving it into view. Okay, so there we go. All right, so what I wanted to say is, x NAND y is really the same thing as in C notation, the logical NOT of x logical AND y. Okay, so all right, so what does it look like as a truth table? So this is a starting point of looking at a truth table, not in the sense of kind of the matrix that we looked at before, but in the sense of we have one column for x, one column for y, and then one column for the expression that we want to evaluate. So in this case, we have this column here to evaluate the overall value of the negated AND between x and y. Now, because we got two independent variables, one is x and one is y, x can be true or false, y can be true or false as well, and they are independent to each other. So what that means is when x is false, y can be, oops, okay, one too many. So when x is false, y can be false, but y can also be true. When x is true, y can be false, or y can be true as well. So we have four possible combinations between the values of x and y in this truth table. So now we have to look at the negated AND of x and y. Since x is false, y is false corresponding to this row, the negation of false is true, so the overall expression has a value of true. On this row, we have x being false, y being true. False and true is false, not false is true. And over here, we have x being true, y being false, which means we just flip the order of the true and false. So the overall expression also has a value of true. It is only when we get to the last row, when x is true, y is true, then x and y is true. But since the negation is applied to the conjunction, so we have not true, which means the overall expression is going to be false. So when you look at this truth table, you can see that, oh, okay, so it's kind of like logical AND, except we flip all the true to false and all the false to true. And that is exactly what it is. All right, so if you don't have any questions here, we're going to go back to the notes. So now the question is, why do we talk about NAND? Why is it important? Okay, now if you have taken CISP 310 from me before, you understand why NAND is kind of important. Because in order to implement a circuit to replicate what a NAND operator would do in real life using actual physical devices, you need 2 P transistors and 2 N-type transistors. Okay, so you only need 4 transistors in order to implement a NAND gate. Okay, so that's kind of why NAND is important when we talk about the implementation of logic using physical devices. But in this class, we are not going to be looking at the implementation using physical devices, and instead we want to look at NAND in a very strange way and ask this question. If all you have, okay, let's say in C or C++, if the programming language only gives you one single logical operator and it is NAND, can you do everything else using just one single logical operator? As it turns out, the answer is yes. Okay, as it turns out, you can actually do it that way. So what we'll do is we're going to look at each one of these, step by step. Okay, so the first thing is I just want the negation of x. How can I do just the negation of x using NAND? So as it turns out, the negation of x is just x NAND x. Now, if you don't believe me, okay, which you should not, okay, you can come up with your own truth table to see this, okay? So this one is really simple because we only got one single we only got one single independent variable, which is x, but we have two expressions that we want to evaluate because we want to evaluate the negation of x, and we also want to evaluate x NAND x. So in this case, because we only got one single independent variable and it's Boolean, which means, well, we only got two rows. X can be false or X can be true. So if X is false, not X is true. When X is true, not X is false. But then we also have to look at X NAND X. Okay, so if you look at the table up here, okay, when both values of NAND are false, then the result is true. Okay, so we put a true here. And when we look at the case when both values on the two sides of NAND they're both true, then the NAND is false. Okay, so now we have this little weird truth table, and this truth table, when you look at the column corresponding to not x and corresponding to x NAND x, oh, sorry about that. That's my fault. Sorry about that. And we'll put the entire thing up here. Okay, so there we go. Thank you, Aiden. So when we look at this, we can see how the column corresponding to not x and the column corresponding to x NAND x, they are identical. Okay, you can look at they have the value of 1 and then the value of 0, 1 and then a 0. So that means not x and x NAND x are equivalent expressions in Boolean algebra. So that means they're basically the same. So now that we have established negation, let's take a look at some of the other operators that we are used to. So this is x and y, and the way we express x and y using NAND is x NAND y, NAND, x NAND y. Okay, so that's a little bit kind of ickish, right? But it does make sense because x and y is really the negated version of x NAND y. And from the row before, we know how to do negation already. So what we are really doing is we are saying, okay, let's first compute x NAND y, and then we just have to negate it. But to negate something is to have a value to NAND itself. And that's why this expression here is going to be exactly the same as x and y. Now, I want you guys, okay, this is what some of the ungraded assignment comes in, is I'll give you suggestions, okay, and say, okay, what about you trying to do this one on your own, okay? In other words, I want you to do something like this, okay? Make your own truth table. You can use a spreadsheet to do it. It's easier to use a spreadsheet. So you basically end up with x as an independent variable, y as an independent variable. So when you have two independent variables, you already know what those values are corresponding to, because each one can be true or false independent to the other one. So we already know that x and y can have these specific values as a combination. So what I want you to do is to say, okay, let's look at just a normal x and y, okay, using C notation. And then I want you to look at or evaluate another one, which is x NAND y, NAND y, and this thing NAND itself. Okay, so I want you to basically fill in this table. Let me give you the values that you need to fill in. So all the question marks are the places where you need to fill in. And I know this one is a little bit long, okay, but you can always look up the truth table up here to know, the result of NAND. So this is the truth table I want you to work on if you want an activity, for this class. This is one of these the activities. I'm not going to grade it, okay, because it's somewhat trivial, but it's also a good exercise in order for you to actually fill in a truth table and also to understand why it is useful, okay? So the concept of a truth table is going to be useful in this class pretty much all the way, I would say at least going through 75% of the class. A lot of stuff, we can use truth table for. The last one, okay, which is OR, is a little bit funky because it is X or Y, okay? How do we express X or Y using NAND? Now this one is a little bit strange, okay? Because the first thing we need to do is to say, well, how does AND and OR relate to each other? We'll get into De Morgan's law, a little bit later, okay? Formally, okay? Officially, we'll get into De Morgan's law a little bit later, but it doesn't hurt for me to start to introduce it to you. So basically, I just want to give you multiple exposure of the same concept. So we'll try one at this point, okay? This is called De Morgan's law, okay? So De Morgan's law has two versions. And I'll present you both versions. So one version says, okay, if you look at the negation of X and Y, okay, it really is the same thing. I use double equal for a reason, because single equal in C and C++ is assignment. It changes the value of some variable on the left-hand side. Double equals establishes equality. So I'm saying that this equality is true, okay? So as it turns out, it is the same thing as not X or not Y, okay? Now, does it make sense intuitively to you? Well, to some people, it does make sense intuitively. To other people, it does not, okay? But it boils down to, how do we prove it, okay? If TAC claims something, you better make sure that TAC can prove it. Or better yet, you can prove it for TAC. So in this case, can someone think of a reason to prove the first De Morgan's law? Okay, the negation of X and Y is really the same thing as the negation of X or the negation of Y. So how would you go ahead to prove this? Okay. Okay, somebody just got in and cannot watch the stream because I have already added everybody at the beginning, and this person probably added like really recently. Okay, so I'm gonna add that person to the student role, so that person should be able to do it now. I'm gonna respond. Sorry for spending a little bit of the lecture time to respond to this person here. There we go. All right. So getting back here. All right. And I got some message in the general channel, which is not there anymore. Okay, very good. All right, so back to the topic on hand here. Okay, does anyone want to make a suggestion of how to prove De Morgan's law? Sorry? You can make a table of yep. Both sides and then compare them. Exactly. Truth table. So we got several people making exactly, giving me the same answer, and you guys are all correct. Good job. So we just make truth table where we have X and Y as independent variables, just like this one over here. And then we have one expression, which is the negation of X and Y, instead of just X and Y. And we have another expression, which is the negation of X or the negation of Y instead of this thing over here. And if every single value is the same, on each row, then we know the two columns are the same, or we can now establish that the expressions are equivalent to each other, okay? So I'm gonna leave that up to you guys to do it again, okay? So, okay, I'm gonna even make a note here using comments and say that this is a ungraded assignment, okay? Make a truth table to prove this. There we go. So I'm gonna do a copy and paste because the opposite of this turns out to be true too. So if I take the negation of a disjunction, it is actually equivalent, or you should be able to prove that it is equivalent to the negation of the components, and then we join the components using conjunction. So there are two parts to De Morgan's law. Okay, this is one and this is the other one. Okay, so once again, I want you to use a truth table to prove, one truth table to prove each part of De Morgan's law. And I think it will be good exercise from multiple perspectives. First of all, it is a good exercise to understand what is a truth table and how it is useful. And the second one is to get a very low level understanding of De Morgan's law, because as weird as it may sound to you, it may not be intuitive to look at, it is not the case that x and y is really the same thing as not x and or not y. If you look at the truth table, there's no denying that they are equivalent to each other. So here comes the question, okay, because I know how certain people think, okay. So some people may think, why do I need to know all of this? Okay, I can just learn how to use negation and just stick with this format. Okay, why do I need to know the equivalency between the left-hand side and the right-hand side of the equality? The reason is actually quite simple. Okay, you do not want to be an inefficient and developer, okay, or computer scientist. So what that means is somebody else may express the same thing using this type of expression. So as a developer, you have to understand that this kind of expression really is the same thing as this type of expression. It is going to be very useful in debugging programs, and also it's going to be very important when you want to understand somebody else's code. So even if you don't have any interest into getting into computer engineering or electrical engineering, where De Morgan's law is super useful, okay, it is still useful in just ordinary coding, because now you understand there are multiple ways to encode the same logic in the program. Okay, that makes you a more effective programmer, because now you can read other people's code more efficiently. So there is that. All right, cool. So I'm going to move this window out of the way. So what section 4.1 is really telling us is you don't really need negation, you don't really need conjunction, you don't really need disjunction. You just need NAND. Okay, if a programming language only gives you NAND as a logical operator, that's all you need, because you can implement the other three using just NAND. Now that is really kind of cool. Okay, at least to me, it's really kind of cool. It's also interesting how we got used to extra operators that are not really necessary, and it becomes really important to us that we have to have programming languages having the not, and or operators, even though when we look at NAND, it can actually replace all three of those. All right, so section 4.2 introduces a new operator. It's called implication. So implication is an operator, which is kind of weird to some people to begin with, okay? Because some people look at implication as, well, but implication means, this follows that, okay? X implies Y means Y follows X, right? So it is only used to tell us things that are true to begin with. Well, that is really not the case, okay? So what I'm going to do is, once again, to use my little simple text editor over here to kind of make that point, okay? So the first thing is, by definition, okay? I got a question over here. Induction. So I'm guessing what Joshua is mentioning is induction in the context of induction versus deduction, whether something is induced as opposed to deduced. That I do not know yet. Okay, so I gotta research and find out exactly what those terms mean in this case, induction versus deduction. But from the very low level mechanical way, okay, if I say x implies y, it is an expression, okay? And that's why I can use a double equal as an equality. It is defined to be not x or y. Now this is when I start to use the notation that I talked about a little bit earlier. I'm using the exclamation point to mean negation, and then using the plus to mean disjunction. Now negation, just like the operator precedence in C and C++, only applies to whatever is next to it. So the negation, the exclamation point in this case, only applies to x. And then the OR is actually ORing the negated value of x and y. Okay, this is the definition. Okay, this is the actual definition of implication, which I use this symbol to represent. I'm using 2 bars with the right arrow because when I use a right arrow with only 1 bar, it has a different meaning. So that's why it is important to understand that implies in this case has 2 bars instead of 1. So if it is an operator that is defined this way, it means we can now have a truth table. I can use a truth table to express exactly the same thing. So we got x, oops, lowercase x, lowercase y, x implies y. Okay, when x is false, y is false, x implies y is actually true. And you see the highlight over here because I'm using the extension of MD, which is markdown. So in markdown, the greater than symbol by itself probably has a meaning of some sort. So now we have x being false, y being true, and the implication is true as well. Now we have x being true, y being false. This is the only time that x implies y is false. And then we have x and y both being true, which in this case, the implication itself is also true. So the bottom line is x implies y is just like any other Boolean expressions. Okay, the expression itself can be true, it can be false. Okay, x implies y can be true, it also can be false. If you're having some problems wrapping your head around this one, it is only natural, okay? Because when we use the word implies, we usually use that word when we know that the implication is true, okay? It's not very often when we say, oh, this implies that. But guess what? That implication itself can be false, okay? It's not very often that we use implication in normal conversation where the implication itself can be false. So I will give you an example. The example is actually in the notes too, so let me just kind of refer back to it. All right, so this is the example. So it's kind of absurd, okay? So I'm making a statement, okay? So let's just say that I'm asking every person in the class to give me $10. And for that $10, I'm giving you a statement of wisdom, okay? And this is it. So for $10, I tell you that a blue cat is sick, okay, implies tomorrow is doomsday. All right, so when you look at this, okay, regardless of how absurd the semantic of the words are, you have to break it down syntactically, okay? You have to break it down in terms of the structure. So the word implies is in between, so that means this really is the part of x, okay? When we have x implies y, this is x, and this part is y. So when you look at x, okay, which is this part here, this by itself is a variable, okay? It can be true, it can be false. So a blue cat is sick by itself as a statement can be true, okay? If you can find me a blue cat and it is sick, that makes a blue cat is sick true. On the other hand, if you cannot find a single blue cat that is sick, then that particular statement is false. It can be true or false. Tomorrow is doomsday is just like that too, okay? It can be true, it can be false. Now, I don't really care about the likelihood, the probability of each statement being true or false. All I need to know is each one can be true, it can also be false. So now the question is, okay, you want your $10 back, okay? And now the question is, how do you get your $10 back now that I just gave you some really absurd statement? So the first thing is, okay, in order to get your $10 back, you have to prove me wrong. In other words, you have to prove this entire statement is false to get your $10 back. So now the question is, when is this statement itself, when is the implication itself false? Okay, so we'll look at each combination. So as it turns out, a cat is indeed sick, and tomorrow turns out to be doomsday. Okay, so you cannot get your money back because what I said is true. So this one is pretty obvious. Okay, when a blue cat is really sick and tomorrow really is doomsday, so from tomorrow's perspective, the statement from the day before turns out to be true. Now obviously, if tomorrow is doomsday, that $10 is not going to do you much good, but you get it back. No, I take it back. You cannot get your $10 back. So this is adding insult to injury. So let's look at the second one. The second one says, you cannot, it is not the case that the blue cat is sick. Okay, in fact, the entire world doesn't have a single blue cat. Okay, and it turns out that tomorrow is not doomsday. So now the question is, can you get your $10 back? Okay, so think about this carefully. Okay, what I said for $10 was a blue cat is sick implies tomorrow is doomsday. And what we can observe is that no blue cat is sick. I cannot find a single blue cat that is sick, and tomorrow turns out not to be doomsday. So from tomorrow's perspective, can you say, well, what you said is actually false, I want my $10 back? What do you think? And why do you think that is the conclusion? So I want you guys to kind of think about it a little bit. Maybe for 10 seconds. I'm going to start a timer. All right, so after 10 seconds of awkward silence, we'll take a look at this particular case. As it turns out, you cannot get your $10 back, okay? Because when I gave you this statement, a blue cat is sick implies tomorrow is doomsday, I never said anything about what if a blue cat is not sick? What if you cannot find a blue cat that is sick? I never said anything about that. All I said is, if you can find me a blue cat that is sick, then tomorrow is doomsday. That's what I said. So if you cannot meet the requirement, if the first part of the implication, which is a blue cat is sick, is false, then the implication itself is by default true. Okay, so that's why you cannot get your money back. Okay, what about the next case? I probably can get my money back in this one because it says, okay, from tomorrow's perspective, there was no blue cat that was sick, okay, and tomorrow turns out to be doomsday, and you go like, aha, I'm gonna get my $10 back. You still cannot get your $10 back because, as I said, my statement of a blue cat is sick implies tomorrow is doomsday never said anything about what would happen if a blue cat is not sick. If you cannot find a blue cat that is sick, this implication doesn't say anything about it. So if it doesn't say anything about it, it is by default true. So you still cannot get your money back in the third case, okay, which is this one over here. So obviously I'm saving the best for last, okay? So if a blue cat indeed is sick, okay, and tomorrow turns out not to be doomsday, then you can come back to me and say, Tag, the statement that I spent $10 to buy turns out to be false because the first part of the implication is true. It is meeting that requirement already, but what it is implying did not happen. Okay, this part is false. So this is the only time when the implication is false. Okay, then you can get your money back. And this is why you want to know why implication is important, because you want your $10 back. So are we doing okay at this point about what implication really means as an expression? That it can, by itself, the implication as an expression can be true, it can also be false. Just like AND, just like OR, just like NAND. So I got a few people typing, that's good. In fact, I'm going to take a little screenshot here while people are still typing. There we go. So we got Joshua and Alex both typing at this point, and Sandeep, so that's good. I will wait for all of those. Okay, so Joshua finished typing first, but an implication requires all scenarios are correct. I'm not sure what you mean by that. So let me go back to the text file over here. So with an implication, we got two parts. We got X, we got Y. You know, they have specific names, but I'm not going to use those names. Okay, and then Sandeep said, what about the answer to attendance question? Oh, okay. Yep. What time is it? Oh, it is the end of the lecture. Okay. We'll make an implication. Okay, so we're going to say answer to the role taking question is implication. And I'm going to make that quiz right away so that you guys can answer that. Okay, so getting to Alex. Alex is typed. So X implies Y is still a Boolean operation. We are not establishing anything like X equals Y. It's not like that, okay? So this is the full definition of X implies Y, okay? If X is false, then X implies Y is true. When X is true, the only time when X implies Y is false is when Y is false. It really is defined like this, okay? So every time when I say X implies Y and you don't want to mentally have to understand what implication means, you know, as an operator, what you need to do is to convert the implication to this expression here, which is not X or Y, okay? Because once you convert it to not X or Y, then you basically, in your mind, you're going to look at this and go like, oh, it's just a Boolean operator. It's a Boolean expression. It can be true, it can be false. I just have to evaluate it to find out whether it's true or not. So does that kind of address the question from Alex? Okay, excellent. We are not at the end of the lecture yet. I was mistaken. I was looking at the time. We actually still got half an hour. Okay, so that's good because, you know, we need to keep going. You know, there's a lot of stuff that we need to cover. So getting back to implication, are we doing okay in terms of the meaning of X implies Y? Okay, so once again, if implication as a word is kind of confusing you because the way we normally use the word implies, you know, basically suggests that the implication has got to be true. So if that is confusing to you, then what you need to do is every time you see X implies Y, you convert it to not X or Y. Okay, so that's one little trick you can do in your mind so that you do not look at implication in a more colloquial way, and instead you look at it as an expression. Okay, now implication is super important in this class. Okay, we are going to see implications a lot. Okay, so it is very important that we clear up the concept of implication at this point, because, you know, a lot of other definitions rely on implications. So we are moving on to the last portion of this module, which is equivalence. So equivalence, you know, is basically the same thing as, okay, this is how it's defined. If I say that X is equivalent to Y, then it means X implies Y and Y implies X. Okay, So if you work out the truth table, it's really kind of simple. Basically, in order for the equivalency to be true, x and y being the same will lead to the expression being true. If x and y are different, then the equivalency itself is false. So that's how equivalency is defined. So I'm going to give you guys a little bit of time to ask questions, because I think between implication and equivalency, there might be some questions. So I'll give you guys like 20 seconds to ask questions. And meanwhile, I'm going to make the quiz for taking roll. And you guys know the answer already. Oh, I guess I have to do it this way. All right, so for roll taking purposes, it is going to be 1 day since the beginning of the synchronous lecture. So you guys have until tomorrow, which is August 26th, 10:30 a.m. to complete this activity. And then I need to add a question to it too. Oh, I don't need a question because it's not a quiz, it's an assignment. So the submission is just going to be, the thing is tomorrow is not doomsday. The thing is tomorrow is not doomsday correct. I'm not sure what it is, what you're asking, Aaron. So we got Aaron and Gary typing for the quiz. Oh, for the quiz, it is implication. The word is implication. I'm going to do it again. This time I'm going to add it as a quiz because quizzes are automatically graded, so I don't have to do it. So I'm going to call this roll of 2020-0825. And I'll put it into assignments for now, but I will change it later. All right, so let me change that. Oh, I have to click on it first. Then edit. August 26, 10:30 a.m. August 26, 10:30 a.m. And I can now put in a question. There we go. And the question is going to ask for a short answer. Fill in the blank. Matching. Essay question. Fill in the blank is fine, I suppose. Okay, what is the word for taking roll? And the answer, and you guys can see it, right? I mean, this makes it super easy for people who are with me right now. It is implication. So there we go. And save and publish. All right. It is implication, singular implication, Aaron. All right. And let me do one more thing before we continue with today's lecture. I'll make it really easy on you guys by allowing multiple attempts and keep the highest score. And if I don't specify the number of times of the attempts, it is basically just infinite. You guys can do it as many times as you want. But I'm not going to let people see the correct answer, so people cannot just submit something and then see the correct answer. There we go. Save. All right. So I would just kind of do this right away, if I were you. Okay, so I'll give you guys some time to do the role taking quiz, and I'm gonna move on to the next slide. So this gives me some time to move on and gives you some time to basically get the role stuff done. All right. So are we good? Are we ready to go? If someone still needs a little bit more time to finish the role taking quiz, let me know. And if we are good to go, then we'll go ahead and proceed. I'm not seeing anyone requesting more time, so I am going to move forward and start to talk about set theory. So you can see this one has not been regenerated recently. This was generated about 3 years ago, so it doesn't have the same feel and look. I can regenerate it later. So we are now starting to talk about set theory, which is a very crucial concept in this class. So a lot of other concepts build upon what we understand about set theory. So let me just take a quick survey. Okay, how many people have some exposure to set theory prior to this class? So I'm gonna give you guys maybe 5 seconds or so to answer the question. All right. So most people do not have exposure to set theory prior to this class. Some people have heard of it. Okay, that's interesting, but that's fine. Okay, we'll talk about set theory and also the terminology applied to set theory right here. Okay, so that's partially why we got actually we have about at least 2, perhaps 3 modules on set theory. So that's partially why I have all of these things typed. Maybe in linear algebra they talked about set theory a little bit. Yep. Yep. Anytime you see the word set, it relates to set theory. All right, so we'll start from here. Okay, we'll start from the very beginning. I just wanted to do a survey. I'm not trying to make any assumptions. All right, so we'll start with section 2. It talks about what is a set. So if you want to imagine in your head what a set is, let's not think about these in abstract terms. Okay, the easiest way to do it is to open up your file explorer in Windows. Okay, a set is like a folder. It really is. Okay, so just in your mind, okay, think about a set as a folder. It's a container. Okay, now when you look at a folder, okay, first question is, can a folder be empty? It doesn't have anything. The answer is yes. Okay, a folder can be empty. So can a set. Okay, so when a set is empty, guess what its name is? I'm just glancing at the empty set. Exactly. Okay, so you guys got the right idea. So a set that doesn't contain anything is an empty set, just like an empty folder. Okay, so the second question is, can I have multiple things in a set and they are actually the same? In other words, I'm asking you, in a folder, can you have multiple files of the same name? Now, we are talking about a normal file system here, so we are not talking about some strange file system where you can have it. The answer is no. Okay, very good. So now we have understood 2 really important aspects of a set, okay? It is a container, okay? It can contain, a folder can contain files, right? It can be empty, okay? A folder can be empty, and so can a set. And then the more important part is whatever is contained inside a set has to be unique. It can only be counted once, okay? A particular value can only be counted once in a set. It cannot appear multiple times inside a set, just like you cannot have multiple files of the same name in a folder. All right, cool. So I think we have just cleared up, some really important aspects of what a set is. It is a folder. So now the question is, what can we put inside a set? Okay, what can be elements in a set? Okay, so elements in a set can be just about anything. Okay, any value is okay with only one single restriction. A set cannot be its own element. Wait, hold on a second here. This makes sense because a folder cannot be in itself. Okay, does that make sense? Has anyone ever tried to make a folder as a component of itself in Windows? You basically do a Control-C, a copy, right? You double-click the folder, and then you paste it into the same folder. What's going to happen? You can put a shortcut, which is not the same thing. A shortcut is a reference to something, which is not the same thing as that something itself. A shortcut is basically a file itself, which says, hey, I'm just a placeholder. I'm referring to that guy over there. Okay, so a shortcut is okay. Okay, you can put a shortcut of a folder within that folder itself. Okay, but you cannot have a folder itself being its own component. So it's not so much as an infinite recursion. It just doesn't work. You got an error. So, all right, cool. Omar actually gave it a try. So what is the error? What does it tell you? I'm guessing you're using Windows. All right, so the error message does make sense. Now, let me try to do this in Linux, okay? And I'll do it on the command line so that this way we can actually see the error message. So in the temp folder, let me just go ahead and make another folder. We'll say test dir, okay? Test directory. And I'm going to copy -r, which is recursive, test dir into test dir itself. And it says, cannot copy a directory test dir into itself. Isn't that cool? And the same concept is true in a set. So a set cannot be its own element. Okay, so that's basically how we understand what a set is. Okay, because it shares a lot of properties of what we already understand about folders. So Aaron is typing something. Let me. All right, so Aaron typed, is there ever a time where you can do something like that? Having an item inside itself. I'm guessing not. Okay, there are cases even in real life that kind of looks like that and feel like that. If you have two parallel mirrors, okay, the mirrors will mirror the image of each other. So you basically end up with a quote-unquote infinite reflection in that case. So that's kind of the closest example that I can give, that relates to this. Okay, very interesting questions. All right, so now we move on to notations. So the notation part has to do with, so if I want to tell people that certain things are inside a particular set, what do I use as quote-unquote language or syntax to let people know that this particular set has these particular elements as a part of it? Okay, so the notation is right here. It says t equals 2, and then this is a brace, okay, or most people call it a curly brace. So it is what is inside a set is delimited, okay, it's enclosed within braces. So within those braces, we use a comma-separated list of the items inside that particular set. It is not, in a way, it's similar to an array, but it's not, because how you order the items inside the braces is irrelevant. In other words, there's no such thing as ordering within how we list elements inside a set. Okay, so let me give you some examples. Okay, so switching back to here and going back to my markdown file. All right, so Aaron is typing something here. Can a set hold both doubles and int? The answer is yes. It can hold anything, okay? So without any explicit restriction of what you can and cannot contain in a set, if you're just talking about defining a set, okay, it can have anything, okay? So let's say, you know, we have a set over here. The first thing is, if I only have 3 numbers, 1, 2, and 5 in it, then T really is the same thing as 2, 1, 5, because the ordering is not important inside the braces. Inside the braces, which means, you know, we are looking at the composition of a set, there's no ordering within those things. Now, when we type it, obviously we have to type something first, okay? But when we look at this, but there's no significance assigned to the actual ordering. So basically, you know, if you look at, you know, different sets, okay, so 1, 2, 5 as a set is completely the same as 2, 1, 5, which is the same thing as 5, 1, 2, and so on. And Joshua is typing something. Is there any difference from a class? Every T has those elements. Well, a set is not a class. I'm guessing that class is referring to object-oriented programming class. Is that correct? Yeah, so a class is interesting because, you know, a class can have properties or members, and each member of a class, okay, so if you look at when you look at okay, that I just lost the word in my head. When you look at members inside a class, they are sort of like elements inside a set, meaning that you cannot have 2 members of exactly the same name inside a class. But a class is different in many other ways, because a class is a template. You use a class to instantiate objects, and a set is not like that. A set really is just a collection of things. Like in this case, okay, if I define T to be the set of 1, 2, 5, that's all it is, okay? You know, we are basically just saying, oh, we have a really small set here. It has 3 elements, and the 3 elements are 1, 2, and 5, okay? Now, and the ordering is not important, okay? So we just know that 1 is an element of T, we know that 2 is an element of T, we know 5 is an element of T, and that's all we know, okay? T has these as elements, okay? So a set is really just a collection, just like a folder, okay? Just like a folder containing files in this case. Are we good so far in terms of, you know, what a set is? And it has elements. Okay, all right, very good. All right, so this is where things get a little bit tricky, okay, in terms of how I would explain it. Because the notes already has the notation, so I don't really have to retype it. So in this case, if I define T exactly the way it is typed here, then this particular T is defined to have 12 as an element, 5 as an element, 2.2 as an element, 7 as an element, -1 as an element, and then 10 as an element. And we can do some counting, okay? We can now say how many elements are in this particular set. That is also called the cardinality of a set, okay? The number of items inside the set is called the cardinality of a set. We'll see that word later. So in this case, we got 1, 2, 3, 4, 5, 6, okay? So T has got 6 different elements. If you want to say, you know, so when, okay, so let's take a look at this expression here, okay? it is 2.2, and then we have this kind of weird looking E, T. That is an expression, okay? It is not assuring, it's not asserting that 2.2 really is an element of T. It is a Boolean expression of asking 2.2 is an element of T. Is it true or is it false? Okay. Now, in this particular case, because of the way I define T, 2.2 is in fact an element. So 2.2 is in T is giving you a value of true. On the other hand, if I ask 23 in T, and I look at this as a Boolean expression, then the value of this Boolean expression is false, because the way I define T as a set does not include 23 as an element. So is that concept clear? That this is really just a Boolean expression. It can be true, it can be false, depending on the membership of a particular set. But whatever is on the left-hand side of the symbol is considered a potential element, and then whatever is on the right-hand side of the symbol is the set in question. So do we have any questions about the in operator that looks like a weird looking, it looks like a weird looking E? Any questions about the notation? Okay. No questions. All right, very good. So food for thought, okay, which is section 2.1. How would you implement the concept of a set in C and C++? Now, I know some of you have taken CISP440 or is concurrently taking CISP430, okay, because it's a co-requisite, okay? I'm just checking here. So some of you have heard of the template class called set in the standard template library of C++. So yes, C++ has that. But that template library actually has a very severe limitation, because when you use a template library, when you use set, you have to say this is a set of whatever type. So you can make a set of integers, you can make a set of strings, you can you can even make a set of a particular class that you define. But you do have to supply the equivalency or the equality operator. So this way we do not put duplicate items into a particular set. But in mathematics, in the most general sense of a set, okay, a set doesn't have any limitations of what it can contain. Not all elements of a set need to be of a specific type. So if I want to, I can define a set, let's say it's S, okay, so I don't confuse with T, which is already defined in this context. So I can define this to have numbers, okay, so I can have 3.14. I can say it can contain negative values, okay, so -2. I can say it can even have a string, okay. And guess what? I can say that it can have even a set as its member. Okay, maybe an empty set. Ooh, okay, this looks kind of weird, doesn't it? Okay, or does it? Does that look weird to you guys? Do we want to have a more discussion about this? It is. Okay, so a dictionary of Python is a collection kind of like this, okay? But it's not weird, okay? It is not weird in the sense that if you think about a folder, okay? So I just make a folder. Can I put a Word document, an Excel spreadsheet, a plain text document, and another empty folder into that folder? Can I make that? Absolutely, right? So in other words, in the general sense of a folder, what that folder can contain as its components, there's really not a whole lot of restriction. The only restriction really is the folder itself cannot be its own component. That's really the only rule. Other than that, we can say, hey, I want to create this Excel spreadsheet file that has a whole bunch of data as a part of this folder. and I have this massive Word document, and then I have this really long PDF file, and then I have this empty folder. They're all components of a particular folder. It is not a problem, okay? So that's why this is not an issue, okay? We can actually say, we can define a set like this, okay? So now when we ask questions, okay, now we have to be a little bit more careful, because now we have to say 3.14 in S is true, okay? So I'm using the word in to represent that kind of weird looking E symbol, because that's how actually we pronounce that symbol, is in, okay? Or if you like to use the long version, it is quote unquote is an element of, okay? But that's really long, so in is fine. So are we good so far? So we can now also say, the empty set in S is also true. Let me give you a trick question now, okay? So the trick question is the set containing -2 in S, okay? What is it? What is the question mark? Is it true or false? It is actually false. It is false, okay? Now, if I ask, is -2 itself in S? That is true. But the set containing -2 in S is actually false. Because what this part here is representing is equivalent of asking, is there a subfolder containing the -2 file in the folder that we have just defined up here? And the answer is no. There's only one subfolder inside S, and it is an empty subfolder. We do not have a subfolder that has a value of 2 in this particular folder that we call S. Okay, so that's a trick question, okay, because I want you guys to think about, when we look at -2 as a value, is it an element of S? The answer is yes. On the other hand, if I put -2, a value, into a set, and then we ask whether that particular set is an element in S, then the answer is no, okay, it is false. Are we okay so far? Or do we need more discussion about the operator that is called in, or in the long version, is an element of? Alex is typing up something. And so is Sandeep. All right. Oh, okay, that's all right. And so everything seems okay according to the text channel. So I'm going to go back to the notes here. So section 3 is kind of interesting. How do we know that 2 sets are the same? Okay. Now this is something that is not easily applied to folders. You cannot. Okay, I shouldn't say that. It's very seldom that we want to look at 2 folders and ask whether they are the same or not. Now, the only time when it is applicable is when we look at a zip file, and then we ask, if I compare this zip file and its content to an actual folder sitting on my hard drive, does it contain exactly the same content? Okay, so there are cases where we actually want to establish equivalency of folders, okay? Because if I want to back up all my class-related files, I want to look at the archive and ask, do I have all the same files in my archive as on my hard drive? Because if they are different, I better make sure that I resolve those differences and make sure that I have an accurate backup of my drive. So how do we compare 2 different sets? Okay, so that's the question. So we'll go ahead and read these sentences. A set can be compared to another set to see if they are the same. Okay, so the key here is we are not trying to determine the ordering. We just want to know whether they are the same or not. Okay, so there's no greater than or less than. We just want to know, are they the same? Do they equal to each other? Unfortunately, at this point, we kind of lack the mathematical notation, because in order to define equivalency of 2 different sets, we need to rely on quantifiers. Now, quantifiers are things that read like for each, there exist, for all, that sort of thing. So we haven't really talked about that yet. We will talk about those concepts, just not yet. Okay. So for now, we'll just go ahead and basically say that two sets are considered the same when every element in S is also in T, and every element in T is also in S. That's the best I can do at this point, because I have not introduced the language that is needed to express for each, for all, and there exist. Okay? But it kind of makes sense. Okay? So when you want to think about equivalency of two different sets at this point, just think in your head and you say, I want to back up a folder that has all my homework assignments and whatnot. I need to check or make sure that the archive file contains the same folder structure and all the same files, and the content of the files should be the same. That is what you need to kind of keep in mind, is that is how we compare whether two sets are the same or not. Okay. So section 4 talks about something that we have already touched on, which is asking whether a set can be an element of another set. And the answer is yes, okay? And it works well with the analogy of folders, because a folder can be a component of another folder, which is fine, right? So this question mark here is referring to section 3, except I probably made a mistake in the back reference, so it could not resolve it and just appears as question mark. All right, so let's go ahead and take a look at this particular definition here. X as a set is defined to have, okay, first of all, how many elements are in X? Okay, so I want you guys to think about this first. How many elements are in X? Now, the trick is to think about X as a folder. Okay, so if you think about X as a folder, how many things are in that folder? The answer is 3. Very good. Okay, so you guys are getting the concept. Excellent. Okay, so we are not recursively traversing and say, under this entire directory tree, how many items do we have? That is not what the question is asking. I'm simply asking how many things are in a particular folder. You double click on the folder and you just count. Okay, we got A, we got B, and we got another set. Okay, now whether that set has nothing or an infinite number of items, it doesn't matter. It is just a set. That set becomes just a single component or element of the containing set. So in this case, X only has 3 elements. A is an element, B is an element, and the set of 1, 2, 3 is considered just a single element from the perspective of set X. Okay. Now the question goes a little bit further than this. Okay, it's asking the question. Remember, in is an operator. So when we ask the question 1, 2, 3 as a set is in X, we are really not confirming. We are really asking, is that true or not? And in this case, it is true. Okay, the set of 1, 2, 3 is in X is true, because we can see how the set 1, 2, 3 really is, an element of X. So are we still doing okay so far in terms of the kind of confusing concept of a set can contain another set? Cool. All right, so we are running out of time. Okay, so don't leave just yet, because I want you guys to read ahead of me. So we are close to the end of basic set theory. On Thursday, we'll definitely be moving on to basic quantifiers. So what I want you guys to do is to read ahead of me. Okay, if you can read the entire basic quantifiers, prior to Thursday's class, that would be great. Okay, so aside than the role-taking activity for today, there is no actual homework assignment other than the ungraded assignment. So remind me on Thursday to go back to the ungraded assignment so I can actually finish that, so that you guys can see what the truth table would look like. But I think most of you got it already, but it doesn't hurt for me to go over that. So are there any questions before I end today's lecture and then I start the office hour right after? Okay, I'm not seeing any questions. All right. So in that case, I'm going to